The last thing we need to work through are the active transport mechanisms. Your cells, all the cells of your body, they will use passive transport whenever they can. Whenever can they? They can when they want to move a molecule in the direction of its concentration gradient, meaning from higher concentration to lower concentration. So let's just make a mountain here. There's going to be high concentration up here. And then down here, there is low concentration. If I want to move things this way, from high to low, or move the water from the top of the hill down into my city, I am allowed to use passive mechanisms. And whenever your body is moving molecules from high concentration to low concentration, your body will use passive mechanisms. But there are times when your body needs to move something from low to high. And whenever things have to go from low to high, it needs to use an active mechanism. Okay? So your body only uses active when it has to. When does it have to? When it's trying to move molecules from an area where they are in low concentration to an area where they're already in high concentration. Why do they ever want to do that? A big story about why they want to do that will be found when we do neurophysiology. Understanding how nerve cells create action potentials, you got to know facilitated diffusion and active transport. Right? So active transport. Active transport requires the cell to use its own energy, its own ATP, and it is the only way to move substances from an area of lower concentration to an area of higher concentration. Let's look at the situation over on the left. There are 4 of these little things inside, only one outside. Frankly, the ones inside would like to leave. If there were a facilitated diffusion channel here, they'd be gone. But they're not allowed to leave because they can't go through the phospholipid bilayer. So they're trapped. And even worse, there is this protein. This represents a protein. This protein is an active transport protein, and active transport proteins are very often called pumps. The one that we're going to learn about with neurophysiology is called the sodium-potassium pump. Guess what it moves? Sodium and potassium, right? If you know anyone who gets heartburn and takes indigestion pills, they might take proton pump inhibitors. They are inhibiting a protein that pumps hydrogen ions, protons, a proton pump inhibitor, right? Man, you can really annoy your family members so much just by knowing a few details. So active transport proteins are also very often called ATPase. And you're like, wait, if it's an ACE, doesn't that mean it's an enzyme? Yes. Technically, since active transport pumps use ATP, they are dismantling the ATP in order to get the energy to do a thing. So technically, they are an enzyme that destroys ATP. So they're often called both. So don't get confused if you see sodium-potassium ATPase or sodium-potassium pump. One's the official name, the other one's the common term. Both mean the same thing. And what does it do? It grabs something and forces it to go where it doesn't want to go. Now, why does life need these kind of pumps? So let me show you something that I'm going to talk about again. Let's just try a blank slide. Okay, so here's going to be our cell membrane, right? And this is what your body does in order to make an action potential happen. Okay, I'm going to totally simplify it. But it is going to force sodium to leave. Okay, and now there's going to be lots of sodium. How did it force it to leave? Active transport. By the way, this red line, that is going to be the cell membrane of a nerve cell, phospholipid bilayer. This is going to be in, that is going to be out, okay? So a nerve cell is going to force, using active transport, force sodium outside the cell. Now there's tons of it out here, and all of it's like, I want in, oh, please let me in. Why won't you let me in? But the nerve cell will say no. And the only thing that's going to change its mind is when it opens up, open, when it opens up a facilitated diffusion channel. And when it opens up the facilitated diffusion channel, that's just a door saying, hey, sodium, go in wherever you want to go. But where does sodium want to go? Sodium wants to come rushing into the cell, and it comes rushing into the cell. So as you're thinking thoughts, as you're moving your fingers, as your eyes are perceiving light, this is happening all the time. Those cells are forcing sodium out, and when the moment is right, letting them run back in. So it has to do with active transport and facilitated diffusion. If only my penmanship were better, I apologize. Let's just answer a couple more questions. So what is facilitated diffusion? What is true about facilitated diffusion? Pause me, take a moment. I'm going to answer the question, okay? Does it use cellular energy? No, because it's diffusion. Diffusion is passive, no cellular energy, okay? So it can't be this one, all right? Does it move molecules from areas of high to low concentration? Yes, it does, okay? Does it move them from low to high? No. From low to high, that would take active transport? No. Does it require special proteins? Frankly, yes, it does. So the correct answer is 2 and 3 are true. Okay? One more. Active transport. Active transport. Does it use cellular energy? Yes, it does. Does it move molecules from areas of high to low concentration? No, right? Because the body would not waste its energy doing something it can get done for free. So no, right? Does it move molecules from areas to low to high? Yeah, that's why we have active transport, is to move from low to high. So yes. Does it require special proteins? Yes. So no, yes. The correct answer is 1 and 3 and 4 are true. Good deal. Now, the last little thing that we should talk about would be endocytosis and exocytosis. Okay. Endocytosis is bringing things in. Exocytosis is sending things out. Endocytosis comes in 2 types. Yeah. The reason why I go, meh, is because the cells of the human body do very little endocytosis. Endocytosis would be like, like the blob, just wrapping itself around me and swallowing me up. And human cells really don't do this very much. We do have some cells in the kidney and some cells in the intestinal tract that do pinocytosis, which is cell drinking. And we do have some cells, mostly just white blood cells that are part of your immune system, that do phagocytosis. But human cells don't do this very much, all right? However, this exocytosis, spitting molecules out, oh, holy cow. Our body's doing this all the time. Cells of our body's doing it all the time. And we're about to talk about the endocrine system. And the endocrine system, this cell right here, would be busy making hormones, packaging them up, and boom, exocytosis. This happens all the time, right? And endocytosis is going to require special proteins, because if at this point I haven't convinced you of it, proteins do almost everything, right? That's it. We're moving on, I think, to the endocrine system.